All right, sound waves. This is my favorite thing about waves. I love sound waves. We're gonna start with sound waves. What is sound? Okay, sound is produced when an object vibrates. Okay, sound is produced when an object vibrates. And sound waves are compressional waves. Compressional waves. Okay, so remember, compressional ones are the ones like where we had the slinky, and we didn't make the up and down waves. We just kind of pushed it in and out. So you would have sections almost like here, where some of them would be kind of thicker areas or denser areas, and then sometimes it was less tightly packed areas. Okay, does anybody remember what the dense or the super compressed areas of a compressional wave was called? What are the compressed areas of a compressional wave called? How did everybody answer at once? Right here.
I'm thinking of rarefactions, but I know that's not how it's said.
Rarefactions are the ones that aren't tight. So those go right here. These are the rarefactions. Those are rarefactions, okay? So I'll say it one more time. Listen to me very carefully. What are the compressed areas of a compressional wave called? Oh, good grief. Has it been that long?
Yeah.
They're called compressions. Compressions.
Oh my God.
The compressed areas of a compressional wave are called compressions. Yes, you guys do that. We just haven't talked about it in a minute. All right, so when we talk, even like if you put your, we're talking right now and you put your fingers on your throat, you can feel the vibration. So when we talk, sound is produced because our vocal cords are vibrating. So like right now I have my fingers on my throat and I'm talking and I can feel the vibration. I can feel the vibration, okay? All right, so everybody good on this? I'm gonna go to the next slide. All right, we'll get like a little bit in, then we'll stop for lunch. All right, if you put your hand over a loudspeaker, whether it's in your car or at your house, you can feel it vibrating. So speakers work by a series of compressions and refractions traveling from the speaker to your ear. So you can see like this area is super, let me use my spotlight here. This area is super like dense. This would be a compression. And then the area under that, this would be like a rarefaction. This would be a rarefaction, okay? So the compression is where it's like a hole, but it's really red, super tightly packed, okay? And then the lightly redded area, little particles, would be like a rarefaction, okay? So the speaker is vibrating outward, pushing air molecules together, and then inward, allowing air molecules to separate. All right, because sound waves fall under the category of mechanical waves, remember M&M, they need to travel through a medium, right? Sound waves cannot travel through empty space, cannot travel through empty space. All right. All right, I want to show you this quick video and then we'll pause for lunch, okay? All right, so watch what happens when sound waves travel through a liquid medium. Turn sound on. So you can see on these, as the speaker is moving, the air is usually doing the same thing, but now it's just traveling not air, but through a liquid. So now we can actually see it traveling through. Okay, so you can see the sound waves going through the liquid, all right? You can see when they change the frequency, they added food coloring so you can kind of see it. Okay. All right, that's probably good. You guys can see the waves actually moving now though. Don't know where that guy came from. Okay. All right. So when we come back from lunch, we'll start up with the speed of sound, but I'll go ahead and put this up and we will finish up when we come back from lunch. All right, so now let's talk about speed of sound. Speed of sound. So the speed of sound depends on the medium. Remember, medium is just a fancy word for matter through which it is traveling, okay? So sound occurs when an object vibrates. So I have a question for you. Before it goes off. All right, so if you look at the pictures below, which one do you think the particles would vibrate the most? Which one would be the easiest one for it to vibrate with, okay? This would be
Solid.
What'd you say?
Solid.
All right, Lydia says solid. You guys can make a guess on your notes, okay? You can make a guess on your notes and then we'll see if you are correct. Okay, so make a guess. Lydia says solid. And that's what she says. Okay, so you can take the, I think you have a little circle on your notes, right? And I think you can just slide it over what you think it would. Do you think it travels the fastest through solid, liquid, or gas? And which one you think it travels the slowest through? So just take your little, I think you have a little circle right here, 2 circles. Take it and slide it over what you think it would travel fastest through. Sorry? If you don't have circles, do you have circles? Are you on
like 3 ovals.
Yeah, there's little ovals. Okay. All right, so Lydia said she guessed it would travel fastest through solid. Let's just see if she's right. All right, so this is just your guess. You just pick your guess, okay? All right, so let's see. All right, speed of sound. Sound occurs when an object vibrates. Speed of sound depends on the medium through which it travels. Sound waves travel fastest through solids. You were right, Lydia. They travel fastest through solids because the molecules are already super close together, okay? And since they're closer, then the energy can travel faster from molecule to molecule. So if we're depending on it vibrating, it's easy to go from one molecule to the next because they're already touching. So the energy can just pass from molecule to molecule. That's the easiest. Okay, and it would travel slowest through gases because those particles are farther apart. Okay, those particles are further apart. All right, so I'll stay here for a second so you can get these down and then I'll go to the next slide. All right, so now that we know that the sound travels fastest through solids, slowest through gases. All right, go to the next slide. Speed of sound. All right, so what do you think would happen if we increase the temperature of the medium that the sound waves are traveling through? Okay, so let's just say the particles are moving this fast, okay, like this picture down here. All right, and then we increase the temperature and they started moving faster. Do you think the molecules would move faster or slower? Faster. We talked about this before. We said that when we think about temperature, all it means is if you increase the temperature, it means that the particles are moving faster. So with that being said, when the temperature increases, it means molecules are moving faster. Okay. The speed of sound increases when the temperature increases. Okay, so again, just to recap, things get hotter, you increase the temperature, things will move faster. So the speed of sound will move faster. Okay. All right. So the next thing we're going to talk about is intensity. Intensity. All right. Intensity is the amount of energy. So remember when we're talking about waves, all we're talking about is the fact that we are moving energy. Okay. That's what waves are. Okay. It's the movement of energy. Right. So when we talk about intensity, this has to do with the amount of energy that a sound wave can carry. Okay. And that's
I'm
related to
so
amplitude.
sorry. Could you go back?
Yes, I can go back. Sorry, give me 1 second. Here you go. Let me know when you got it down, okay? All right, here we go. All right, so intensity. All right, so we were saying, I was saying, this has to do with amplitude. Now, remember when okay, here's the interesting thing. With sound waves, they are compressional waves, okay? Now, when we're talking about amplitude with transverse waves, it was easy because amplitude was how high it was. Okay, so this was my amplitude like this. But for these, okay, that's not the type of wave that sound is, so we can't use that. It is still related to the amplitude, okay? But the amplitude is based on density, okay, for a sound wave. So if you have a quieter wave or a quieter sound, then it does not carry as much energy as louder waves, okay? So for compressional waves, the amplitude is based off of the density. So density is like how tightly packed the particles are. So like for instance, when you're looking at, when we're looking at this, these are both, sorry, trying to get my little spotlight here. These are both compression waves. So here's a compression wave and here's a compression wave. And even though this is a compression, this is a rarefaction, this is a compression, this is a rarefaction, same thing down here. This compression has a lot more particles in it than this compression, okay? This compression has a lot more particles than this one. All right, so this one has a higher amplitude. This one has a higher amplitude. All right. I'll give you a second to get that down. All right. Next slide. Now we're going to talk about, we're going to get to the point where we're going to be talking about loudness in a second. Intensity is the amount, where I put it up, is the amount of energy that flows through a certain area in a specific amount of time. All right, intensity is the amount of energy that flows through a certain area in a specific amount of time. This influences how far away a sound can be heard. So, for example, if I increase the intensity, okay, then you should be able to hear me yell from further away. If I decrease the volume, you decrease the intensity. The example would be whispering, okay? So if the sound wave has low intensity, that means it does not have a lot of energy or it has less energy. And because it already started with less energy, it's going to also lose energy more quickly, okay? More quickly. All right, loudness. This is basically what we think about when we think about the volume, like when we turn stuff up or turn it down. Loudness, though, is actually the human perception of sound intensity is loudness, okay? So how we perceive it. So it's really very subjective, right? Me and Jordan could be listening to the same song and I could be like, oh my gosh, why does he have this so loud? And to him, he could be like, this is like the normal loudness that I listen to stuff to. So loudness really is kind of subjective. It's the human perception of sound intensity, okay? So it's like, this sounds really soft, this sounds really loud, all right? But if you increase the intensity of a sound, okay, then the loudness that you hear increases. So even though I could increase the intensity and it could be louder to Jordan and louder to me, what we actually perceive though may be different, okay? The unit for intensity is a decibel, okay? So that's like how loud something is. All right, so you can see like on this chart, we have whispers are very low decibels, 15 decibels. This is the loudness in a normal average home, about 50. Vacuum cleaner is pretty loud, noisy restaurant. All right, once you get past 120, it can be very, very painful for anyone. Okay, so there's two ranges. This is the loudness that we listen to. Below 0 decibels, we cannot hear it. And above 120, it's actually painful. Okay, so intensity of sound is used to describe, use the scale at the right. Volume is essentially the degree of loudness or intensity. Sounds below 0 can't be heard, and sounds above 120 is painful. Okay, sounds above 120 decibels, that's a little d and a capital B, are painful. Like if you ever notice, like if you've ever flown before, the people out by the airplanes, they always make sure that they have on the earmuffs, like the big ear things, so that they're, you know, people be like, oh my gosh, my ears are bleeding. And maybe they're not actually bleeding, but it's very painful to them, okay? Even if you notice a lot of people, if you look at a lot of musicians that play drums, okay, even though they play drums all the time, a lot of times, especially when they're in a studio, they'll actually have on their ear. They can hear themselves still, but they try to protect their eardrums, okay? All right. Pitch and frequency. This is when you guys got to hear how beautiful I sing, okay? So remember we talked about this before. So this is kind of a review. Pitch is how high or low a sound needs to be, okay? So that's related to frequency. The higher the pitch, the higher the frequency, the higher the sound. So if anyone is a musician or a singer, these are the notes, these are low. So it's like, I don't even feel like singing today. I don't want to bless you guys with my talents, but do, re, mi, fa, sol, la, ti, do, like that. Jordan was so excited. You should have seen his face. He was like, wow, I didn't know she could do that. It was fantastic. But do would be the high note. Don't you sing, Lori? What's do? Are you a do, re, mi, or a fa, sol, or la, or ti, or do? Huh? Sing something low.
Glory, aren't you a soprano with me?
That's what.
Yes, indeed.
She said. She said. Do. Wait. Do.
You mean like tender?
I can do like male low.
Okay, let's do something low for us. She said.
Don't do it. Don't do it. Don't do it.
All right, sing something high for us. Oh, see, I actually taught her how to do that.
Yeah.
Miss Peyton, I don't understand these deceits that come from you is ridiculous.
Excellent. And I didn't even try to tone myself for that one. Hold on, let me hit my right here one time.
Miss Peyton, oh my God.
No.
I thought we had trust, Miss Peyton, but we can't have trust if you continue to lie.
Haters.
I hate it when you're
Haters. I'm just saying. I have talent. I have talent, and yet and still I'm here.
I'm not hating on nobody. I didn't say nothing. I'm just kicking.
I was gonna make a joke about how like when you said like when your ears bleed, I was gonna like compare that to your singing, but I decided
No, you were not. No, you were not. First of all, I have the voice of an angel. Okay. Oh, Lord. What? Y'all don't remember my twinkle, twinkle.
For the love of God.
I bet you a big one will be crying.
Jordan is loving this. He
That was
is.
actually pretty
He
good.
is crying tears of joy right now. He is crying tears of
That was
joy.
actually pretty good. Just
Hey, oh, did you hear that? Glory said, "Oh,
Don't just
Thank
not
you.
for that song.
I'm just saying."
Not for that song.
Not that. What?
Like
Okay.
gospel.
Okay, I'll sing out something else later. Okay. Anyway, high frequency, many compressions hitting your eardrum at once. Did you hear how many of my compressions was hitting your eardrum every second? The tears that Jordan had in his eyes from how beautiful I sounded with that, that right there, his heart just melted. I'm just telling you. Okay. All right. Ultrasonic. I know you guys have heard of this. Ultrasonic. This is waves over 20,000 hertz. We can't hear those. It's too high pitched. This is like a dog whistle. Okay. Like a dog, like we can't hear that, but dogs can. There's also things that, did you know there's a thing such as a deer whistle? You can put them on the front of your car and it scares the deer away so they don't like run into your car. So those are waves over 20,000 hertz. Then you have infrasonic waves, which are under 20,000 hertz, and you can't hear those either. So one of these, ultrasonic, way too high for us to hear, and infrasonic, way too low for us to hear. All right. So I'm gonna just show you quickly this little.
I got a question. What about when you rub styrofoam together?
I hate that thing.
I don't know. I've never done that.
Tell me why I literally just heard that in my ear and immediately flinched.
I'm gonna bring some styrofoam and do that.
Oh yeah, see, I won't be coming to your class ever if you do that.
This is basically what I sound like. High frequency.
I can still hear it.
I can still hear it too, but it is. One of them was painful. I can barely hear it.
I still hear it.
All right. Let me. Oops. No. We don't want to do that. No. All right. So, oops. Back to pigeon. All right. So next we did this. Everybody got all this down? Anybody still writing? Okay. Pitch and frequency. We already did that. All right. Doppler effect. Doppler effect. All right. Change in pitch or frequency due to the fact that something is moving. So the perfect example of this
Moving the chair.
is, I was gonna say something, if you're coming down the road that make you pull over, it's like sounds weird as it's coming up to you, but then once it passes you, it sounds weird again. That sound was from a certain type of vehicle. And
You talking about the ambulance?
Yes, the ambulance. That's a Doppler effect. Okay. So it's like, it sounds weird. Okay. And it doesn't matter if the ambulance is moving or if you're moving. Okay. It doesn't matter which one's moving, but because the pitch changes due to the fact that something is moving, that's called the Doppler effect. Okay. All right. The faster the change in position, the greater the change in pitch. The faster the change in position, the greater the change in pitch. All right, I'm gonna play a super short video for you, and then we are almost done, guys.
We are done.
We are almost done.
We are done.
Not quite. All right, here we go.
Stop.
I'm just playing video.
Ow, ow. You'll notice that as the source of the sound moves closer to you, it gets louder. And as it moves away, it gets softer. That makes sense, since the closer you are to the source of the sound, the greater the intensity of the wave that hits your ear. But have you ever noticed that the pitch of the sound changes too? It's called the Doppler effect. As the source of sound moves towards you, the pitch of the sound you hear increases. And as the source moves away, the pitch decreases. To see why, imagine you're standing on the sidewalk when suddenly you hear an ambulance siren start up. It's coming from down the road and it seems to be moving toward you. The ambulance is continuously emitting sound waves at a certain frequency in the form of that siren. But as the ambulance moves towards you, the ambulance is also moving towards those sound waves. So the peaks that hit your eardrums are closer together, even though they're moving at the same speed, and you get hit by them more often, which means that you hear a higher pitched sound. At the same time, it keeps emitting more sound, which adds more peaks to those earlier sound waves that were heading your way. What you end up with is a sound wave with a higher frequency than before. That's what hits your eardrum, so you hear a sound that's higher in pitch than the one you heard when the ambulance was further away from you. As the ambulance passes you and starts to drive away down the road, the opposite happens. Sound waves still coming toward you, but the ambulance is driving away from them. So the peaks that hit your eardrum are far apart, and you hear a sound with a lower pitch. The Doppler effect isn't only unique to sound waves, it happens with light too, which means we can actually use it to measure the distance of stars. But more on that much later. For now, you learned about sound waves and how they move particles back and forth to create differences in.
So basically with a Doppler effect or a train, remember how like you can hear a train far away, it's like no big deal. Then by the time it gets to you, it's like rah! And it's like, oh my gosh, my ears, my ears, my ears. Okay. But then as it moves away from you, again, it's not so bad. Okay, that's the same thing. And it's because, right, and it's because something is moving, whether it's you or the thing that's making the sound. Okay. That's basically what happens. So that's the Doppler effect. Ambulances, police sirens, radar guns that measure speed. And you've heard of the Doppler effect, probably mostly on the weather. So they'll talk about the Doppler, using the Doppler to track storms when you watch the weather. Okay. So this is just an example of it. So it starts out as a low frequency, and as it gets closer to you, it gets higher in frequency. Okay. All right. Super fast review, and then we are done. All right. Parts of a wave. Don't forget this. So I'm going to have this up for you. Okay. But you have wavelength, crest, amplitude, trough. That's for a transverse wave. This is the parts for a compressional wave. All right. Don't forget, this is all the stuff that will be on your test. Okay. Then you have velocity, frequency, and wavelength, and calculations for that. Remember the units for it: wave speed or velocity is measured in meters per second. Frequency in hertz, wavelength in meters. Okay. Don't forget this relationship about as frequency increases, energy increases, wavelength decreases. Remember we used to draw that, right? We talked about the difference between this wave and this wave. Okay, so remember the one on the bottom, higher energy, higher frequency, but the wavelength got way smaller versus the wavelength on this one. Okay, so you need to remember that for the exam as well. Yes, what is your question? You need a picture? Oh, you needed the picture? Okay. Let me draw it again. Okay. All right, Gloria has a question. Let me draw my waves again. Oops. Except for I just went back. All right, here we go. Here's one. I don't know why it keeps disappearing. And here's the other one. All right, what's your question, Gloria?
So, why did it get smaller?
This is higher frequency.
No, I'm talking about why did the size get smaller?
The size is because you get more waves. The wavelength got shorter. So this wavelength is from here to here or here to here. Okay. So because this one got smaller, you started getting more waves. So if you decrease wavelength, you increase frequency and you increase energy.
So as the higher it gets, like the higher the frequency of it.
Yes, higher
It gets
frequency.
smaller and more fast.
Yes. Very nice. All right. All right, super fast. Let's see. We talked about that. Parts of a wave. Electromagnetic spectrum. Remember, Ronald McDonald is very ugly, extra gross. Okay, so we talked about this. Wave behaviors, constructive interference, destructive interference. And then we also talked about reflection, where it bounces off, refraction, where it goes through and changes speed, and then diffraction, where it bends around. Okay. And That's it. This is a review video, but I'm not gonna play it. You guys can watch it on your own time. Any questions?